Welcome to qnawire.
Hi, so in this case, we're going to deal with finding the pH for two different compounds. The first one is a hydroxylamine hydrochloride solution. So this is going to be HO, NH3, Cl minus. This is all going to have a positive charge. In this case, we can omit directly the Cl minus because that is just going to be an spectating anion, which is going to be in solution with water. Of course, this is going to be a weak acid, even though we're given the value for Kb. And this is going to produce HO and H2 plus H3O. So what we have here is the acid and the corresponding conjugate base. But if you realize this reaction corresponds to a Ka, right? Because Ka is going to be concentration of the base times concentration of H3O plus divided by the concentration of the acid that I had originally. So how can I find the K coming from Kb? Well, quite easy. We can get Ka times Kb needs to be equal to Kw. So that means that Ka is Kw divided by Kb. In this case, substituting the values, remember that Kw is 1 times 10 to the minus 14. The value for Kb for this compound is 1.8 times 10 to the minus 8, which is going to give us a Ka of 9.09 times 10 to the minus 7. So the next thing that we can do is employ our ice table in order to get the final concentrations that we require. So the initial concentration that I have is 0.0403 molar. The amount of change that I'm going to get, let's call it x with a negative sign. So at equilibrium, I'm going to get 0.0403 minus x. I'm going to produce plus x of both of these compounds. So x and x. And recall that Ka is equal to concentration of HO and H2 in this case. That is the conjugate base times concentration of H3O plus divided by the concentration of my original weak acid. This becomes x squared divided by 0.0403 minus x. Now we know that the value for Ka is very small, right? We have a value of 10 to the minus 7. That means that x is going to be very small. So we can approximate the approximation of 0.0403 minus x is going to be approximately 0.0403. This is going to be true if and only if x is lower or equal than the 5% of this quantity, which we can verify at the very end of our calculations. Using that approximation, this becomes x squared divided by 0.0403, or, and in a way that you may have found somewhere else, x squared divided by c0, right? So with this, we can solve for x. X is going to be equal to my Ka, which is 9.09 times 10 to the minus 7, multiplied by my initial concentration, 0.0403, and I'm going to take the square root of all of this. This is going to give us 1.91 times 10 to the minus 4. And guess what? That x is the same as the concentration of H3O plus that we have in our solution, equal to concentration of H3O plus. That means that the pH of the solution is going to be simply the minus logarithm of this concentration, right? Minus logarithm of concentration of H3O plus, which turns out to be 3.72 for this first solution. So we're done with the first case. Now let's go for the second one. In the second one, what we are going to have is a lithium fluoride solution. Lithium fluoride solution of 0.0168 molar. And in this case, we're given the Ka. Curiously enough, I think that your professor, what he or she did was give you the inverted ones just for you to calculate Ka from Kb and Kb from Ka in both of the cases. But let's see how this is going to work out. Okay. So for this scenario, we're going to have is, of course, lithium fluoride. It's going to dissolve into F minus. So now F minus can react with water in order to produce HF plus OH minus. And this corresponds to the Kb equation, right? So this is Kb equal OH minus times concentration of HF divided by the concentration of F minus, which is the base. So now we need to find the value for Kb. Same procedure as before. This is going to be Kw divided by Ka. Thus, Kb, it is going to be 1 times 10 to the minus 14, that is the value for Kw, divided by the value of Ka that I have, which is 6.8 times 10 to the minus 4, giving us 1.47 times 10 to the minus 11. Again, we have a very small value. So at the initial point, I'm going to call it directly C0 in this case, just for you to have a very familiar derivation. We're going to have 0 of all of this. Water does not enter equilibrium because it's a pure substance. The amount of change, again, it is going to be minus x, doesn't matter, plus x and plus x. And at equilibrium, we're going to get C0 minus x, x, and x. That means that Kb, it's going to be equal to x squared divided by C0 minus x. We're going to do the same approximation because Kb is very small, is 1.47 times 10 to the minus 11. And the value for C0 is in the order of 10 to the minus 2. So this becomes x squared divided by C0. Thus, x will be square root of Kb times my initial concentration. Let's replace the values. Kb, 1.47 times 10 to the minus 11. Initial concentration is 0.0168. The value for x that we're going to get is 4.97 times 10 to the minus 7. Now, this concentration is not going to be the value for H plus, right? This is the concentration of OH minus. So now we can calculate the POH, which is minus logarithm of concentration of OH minus, giving us a value of 6.3. And we can get the pH using the following equation, 14 minus POH. Remember, this actually comes from taking the logarithm of this equation, essentially. So the result is going to be 7.7. And this is going to be the pH for the second solution. And that will be all. Thank you very much.